Okay, so welcome back. There was one question in the break that I'll just address to everyone. That was a question for the assignment. Can we work together? And the answer is yes, but you have to hand in individually. And now, how does that work? Well, if you copy-paste someone else's report and hand that in, it's not that individual. So I have to see that you can say all the text and comments and things that are there are actually individually written. So what I recommend is that you work together, preferably on your own laptops, and then make the code work that you need to do, make the calculations right, and then you kind of discuss what you want to be doing, how to document things, and then you kind of go apart and then finalize the writing on your own. That's the easy way to get around that. But I also do recommend that you work together. For most of the assignments, I won't kind of say too much if the code is also very, very similar. And search and replace is not sufficient to make it not very, very similar. I've seen that happening. It does almost trick Urkund, which is the system to check for plagiarism. It doesn't trick me. So there are some things there. And I will ask you, but I will get back to that in 2 weeks when you get the first assignment. I will ask you to state on the front page with whom you work with. Because when there is then in Urkund saying that there's 50% similarity between these two reports, well, you declare that you work together. And I'll go in those cases where the overlap is large and check, well, okay, there was a unique contribution from each of them in their individual report. It was just because the output of a linear model with the same input data and the same model structure, bang, you got half a page that is identical. I mean, that is not plagiarism if it's the right model. So there are some gray zones there, but usually it's not a problem. Usually, however, there are some that I tell, that was too close. If they're not more different next time, it's a problem. I've had cases also where I file persons for plagiarism, and then you just fail the course. That's easy. Doesn't happen every semester, but it happens. The worst case I've had is someone that copied a report from someone else. He did not want to type the formula into Word, so he got a screen grabbed that formula from the PDF that he had and pasted it in. When I saw that identical LaTeX set equation in a Word document, okay, that's not what I want. Let me put it that way. Come on, this should work. Does not work. Can I ask you to close the door? Supposed to be a nice feature that I can show here, but apparently it doesn't work always. So, just so that we're all on the same page, a multivariate random variable, how do we define that? Well, we'll use uppercase letters for random variables. When we combine, in this case, n in a vector, we'll make it bold in general. And assume that you've seen the joint distribution function, at least in 1D. When you do it multivariate, well, it's a function of x in all the dimensions, and its probability of observing x1 less than or equal to lowercase x1, comma, 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 up to uppercase xn as a stochastic variable xn less than or equal to the lowercase argument xn there. So lowercase letters generally represents known numbers. In this case, it's a function of something, so it's a known number. Bold indicates vectors, and uppercase are random variables. I think that's kind of standard, but now it's defined in the same way. That was the distribution function from the previous slide. we also talk a lot about the density function, and in the multivariate setting, you just take the partial derivatives with regards to all the dimension, just like in a univariate setting, where you say, well, I have the distribution function, and I just differentiate that to get the density. It's the same thing you do in a multivariate setting. You just look at the slope of the n-dimensional plane here. We will deal with things and write it up in a multivariate setting, and we will also quite often try to do it as a lot of combinations of independent univariate things to make calculations easier. But that will be clear later. Sorry, I have to. That's good. So, and you can of course then, since you differentiate, you can get back from the density function to the distribution function by integrating over the density function. So it's, and in the discrete case, we won't be doing much in the discrete case, but just to state it, the density in the discrete case is defined as the probability of observing the exact observations. But we will, as mentioned earlier in this course, generally always have the continuous, so we will be working in R for our variables, not in discrete values. In most cases, that will be a good approximation. Now, the one thing that we'll use the most time on is the multivariate normal distribution. So, I don't know how many of you have seen this before. The top equation there. How many of you have seen this before? Quite a few of you, but not all of you. That was sort of what I expected. In probability theory, you have seen at least a bivariate version of this, but not the general multivariate version. I'll just write it so that we are, and on the board I will be a little bit sloppy sometimes regarding what is bold and what is non-bold, but I hope you will follow me most of the way there. So I will write it just a little bit different, just to make it more similar to the usual way. So we have the square root of 2 pi, that's what we usually have. And then what is here for the univariate normal distribution? Do you remember what is here? What? The variance, exactly, yes. So you'll have sigma square, typically. So here we'll have the determinant of the so-called covariance matrix. We'll get back to that. And then I need to raise this to the power, to the dimension of the system. So that's the first part, and then comes the exponential part, which is minus 1/2, and then the usual definition is x minus mu squared divided by sigma squared, right? So in a matrix vector formulation, that will be a little bit different here. So we have the x minus mu, that's the usual thing, but now this is a vector. And to pre-multiply that on the inverse of the variance, which is a covariance matrix, we'll get back to these things. We have to transpose it, and then we cross-multiply again by this, x minus mu, and we're done. So that's the definition in the multivariate setting. But it should be easy for you to say when uppercase sigma inverse is sigma square, lowercase sigma square for the univariate case, you say n equals 1, then this is equal to sigma square. Then you can see what you have seen before. Yes?
Why do you raise both square root of 2 pi and the determinant of sigma to the power of n, while on the screen it's only 2 pi? That's also raised to the power of n.
Thank you. Right, perfectly right. This is to the power n, and this is just the square root. because the dimension n is in there. Dimension is in the determinant. Thank you. I wanted just to collect these things, but I shouldn't have. Thank you for that. So the definition, notation-wise, uppercase sigma is a symmetric and positive semi-definite matrix. Also just a covariance matrix, a variance matrix. We'll get back to how that is constructed. The notation, it follows a multivariate normal distribution with a vector of mean values and this covariance matrix. If you have a standard multivariate normal, the mean is a vector of zeros and the covariance matrix is the identity matrix of the corresponding dimension. So that's just like the 0, 1 in the univariate case. And in the univariate case, if you had a standard normal distribution and you wanted to transform it to a something with a mean value and a variance, I don't know if you remember what you did. Yes? Well, reverse. If you have the standard normal and you want to go to something that is not a standard normal, it's a reverse of an inverse of normalizing it. So in the univariate case, what you would have is that if x comes from a normal distribution with some mu and a sigma square here, then you could take, and then we have z that comes from a normal standard normal distribution like this. Well, then you could write x as the mu here plus sigma times, oops, not square, times z. Well, the problem in a multivariate case is that you just take the square root of what is written there. But the square root of a matrix is not defined in the same way as the square root of the number. So you need to make a factorization to get two matrices that multiply together gives you this covariance matrix. But you have the same structure. You can find x as the mean value of x plus some matrix that you multiply on a standard normal to get this. Maybe you also remember when you take a random variable and multiply by a number, what happens to the variance of that standard variable? To be more particular, if you have the variance of x, and in this case, let's just say it's sigma squared, and then you define y as a times x, and then the question is, what is the variance of y? Well, it does have to do with the variance of x, but what has to be written there? Do you remember?
A squared.
A squared, exactly. So when you multiply with something, the variance, you multiply it by the same thing squared in the univariate case. Now, due to dimensionality and things, because that function may reduce the dimension in a multivariate case, we cannot do this. Instead, what we'll do is to have the case down here. Y is equal to a plus bx. You take b and you pre and post multiply it, transposed, on the matrix of the covariance. So in the multivariate case setting, this is n equal to 1, n greater than 1, then the variance of y is a times the variance of x, a transpose. So here it will be y equals not a scalar, but a matrix A times x. So remember always to pre-multiply by A and post-multiply by the transpose, rather than just pre-multiplying by the square of it. That's the, you can say, the only difference when you go from a univariate to multivariate. The mean value there, that is obvious, I would say. And there's a little bit more in section 2.7 on this. Another thing is to look at, you can say, what is the definition of a stochastic variable? Well, typically we want to look at the density. We can look at x and minus x. Obviously they have the same density, but they're not the same variable. So you can have things that have the same density, but it's not the same distribution. Usually I will not construct cases like that. Usually when you do something and make a transformation, it's more than just multiplying by -1. That's too boring in the long run. But just to say that having the density to be equal does not mean it's the same distribution. So, now we get to something a little bit more tricky. Marginal density function. All of you who took the probability course have seen it before, but it's also one of the things that my experience is that not everyone remembers everything. So what is often the case is that you have some data and you do not actually care about everything. So in a general setting here, we will say, well, we care about the first k dimensions, not the last from k plus 1 to n. So we'll look at the marginal density, or define it as a function of only the first k. K could easily be 1. And then we'll integrate out all the other dimensions from k plus 1 to xn over the entire space that we have there. As an example, what we have here is that we have just two illustrations of a joint density function. I'll make a similar drawing down here. I will exaggerate it a little bit more. We can label them x1 and x2. And then I will illustrate the density as some contours, and of course I can draw more, but I'll just stop. Let me make one more. Could be nice ellipses if I had more experience with that. So this is the contour plot, or the density that is plotted here in yellow and red. If I do this up here, what does that correspond to? To get the marginal density, what I have to do, if I want to do it for f of x1, I want to get the marginal density of x1. What I have to do is, by the formula, I have to integrate from minus infinity to infinity the joint density function f, I'll call it x1 down there, f of x1 comma x2 d, and then I should integrate with respect to the remaining dimensions up here. So that will be x2 in this case. So graphically, what does this mean? It means for a given value of x1, say 0, I integrate vertically. So I basically just take the sum of all the probability mass that is along this line here. That is what I do to get the marginal. So that means I take away the dependence on x2 by just saying what happens here. So at any point here, I can integrate what is the integral along a vertical line here. That's what I do. So that is the marginal density. and it looks something like this, as drawn up there. Now, it does not depend on x2. But if I go to what is called the conditional probability, or density, I do a similar thing, but now I will condition. I thought I had to show it. Yeah. So what does that mean? That means that if I, instead of integrating out the entire thing here, I pick a value for x2, say here. If I condition on x2 being this value, then I say what I want to look at is the density of x1 given x2 equals lowercase x2. It's easy to read on the slides. How do I get this? Well, I want to look at what happens to, for x1, what is the density along this line here. If I just take the joint density here and look at this, I can look at the joint density of x1, comma x2, where I'm using this fixed x2 from down here. Is this fine or not? It's a trick question. It's not fine. So, in order for something to be a density function, what should be fulfilled? In any 1D, 2D, any dimension.
Non-negative and integrate to 1.
Non-negative and integrate to 1. Exactly. Let's assume that we're not just non-negative, but we're always positive. That makes life easier. Because if I integrate along this line here, what do I get? What do I get if I integrate along this line? Do I get 1?
Lower.
Sorry?
Lower the 1.
Lower than 1, exactly. So what to do? This is not a density. I need to normalize it with something so that it does become a density. So if I normalize with the integral across this line, it is a density. But we just define that integral along a line there as the marginal density. So I will normalize by the marginal density x2 evaluated at x2. Does that make sense? It's also what is written up here. So that is one example, and that also means that if I take another value of x2 up here, then it's that line I want to look at. So if I want to draw these conditional densities in a similar plot as before, then the red one will look sort of like this, and peaking around there, and the green one will peak a little bit further to the right, sort of like this. So that's the idea by a conditional dense distribution and the marginal distribution. We will use them a lot, but at some point we get used to not writing it, you see, in this complex notation, but in a simple notation. So it's as written up there, it's a joint density divided by the marginal density of, you can say, the variable that you condition on at the value that you condition on. Because of course, if you do it through here, the joint density will reach a higher number than what you have down there. So you need to normalize with the appropriate number. Independence. Well, the verbal definition, if knowledge of x does not give any information about y, then we have that the conditional density here of y given x equals x is equal to the marginal density. So if there is no relation, if I had drawn, instead of ellipses here, I had drawn circles, that would have been the case. Because no matter which x2, the highest point would have been the same. So it would have been the same distribution. Well, that leads to the following definition of independence. X and y are stochastically independent if and only if the joint density is the product of the marginal densities. That's the definition. Expectation, to change the subject a little bit, is what we will do most of this course. We'll do a lot of expectations. I'll explain later why. So x be a univariate random variable with a density, be it marginal density, doesn't matter, or univariate, doesn't matter. The expectation is defined in the continuous case as the integral of x times the density integrated over the space where it's allowed to be. Generally from minus infinity to infinity. And in the discrete case, as usual, the integral becomes a sum, but that's just to have it there, we won't spend much time on it. Now this operator up here, expectation of x, where you just put x in here, is also a linear operator. Which means that the expectation of a sum of things is the sum of the expectations. You also know that if you have a constant multiplied on something inside an integral, you can move that outside. And if you instead of x, put what is written down here inside there instead of lowercase x there, you also know that you can treat that as independent integrals. So it's fairly easy to show this down here. Also to say that there's a lot of things that I could prove, but I won't prove everything that I could prove. That will spend too much time. There was something, yeah. Now, the expectation is what is called the first order moment. But we can also do nth order moment. So before we did x to the first power, now we just do it for the same thing. So any function you put in here, you want to take the expectation of, you pretty much do the same thing. Just put that function in front of the density and integrate over the space. That's how the expectation of something is defined. The central moment is that instead of taking x, you take x minus the expectation. I assume that you've seen this before in some setting where n is 2. In particular down here, the variance is defined as the expectation of x minus the mean value of x, which is the expectation of x squared. So, do you also all remember how to get from there to there? Or should we just do that? So, let's just do it. The variance of x is defined as the expectation of x minus the expectation of x square, end of expectation. Well, I can safely just multiply this out in here. So what do I get? Well, I keep the expectation outside. Consider this as I'm just working inside the integral and just shuffling around terms. So I get an x squared terms. And then, now we might be in a multivariate setting. So I'll write it a little bit different than what you usually would. You have the x on the expectation of x, and you have then minus the expectation of x. Oops, actually this is only the univariate. In the multivariate things I should, well, I'll get back to that in another point in time. And then plus expectation of x squared. And then I close here. Now, what happens here? What comes out of this? We know that the expectation is a linear operator. So the first thing to do is take the expectation of the first term, that's easy. Then we take minus the expectation of the second term here. Expectation of x times expectation of x minus the expectation of x expectation of the expectation of x, I'll write it out all the way, times x plus the expectation, well, the expectation of the expectation of the expectation of x squared. That's too much to say. I would have to say it wrong. Now, if you look at these terms, this one I will keep. When I go to the next term here, the expectation of x is the mean value. So that's a constant. A constant, you can move that outside the integral. So this becomes expectation of x squared. Because what is left is the expectation of x. The same thing happens to the next term out here. Minus the expectation of x squared and plus, well, again, this is a constant in there, so the expectation of a constant is just the constant. So that's the expectation of x squared again. And then these two terms out here cancel out. And we're left with this that we set out to get. There's a lot of rules for calculations with the expectation. I'll get to those in a moment. First, now I just introduced the variance, but there's also covariance, where the covariance between two random vectors x1 and x2 are defined as this is univariate again, sorry. x1 minus expectation of x1 multiplied by the parenthesis x2 minus the expectation of x2. And in a similar derivation as this down here, you can get to the expectation of the product minus the product of the expectations. You also always have to keep in mind what is the order of those two terms. But if you at some point get to something that is negative, the order is wrong. That's the easy one. Likewise, in a matrix setting, if you swap the order, you get something negative, and it's no longer a positive semi-definite matrix. It's not a variance, so you did something wrong. So a simple sign test is sufficient here to check. Or you just look it up or remember it. Calculation rules. Well, the variance is the covariance of x with itself. That's kind of the usual definition. You also have the calculation rule. This is the one thing that you will be using repeatedly in different contexts. So it's the usual multiplication rules that you apply. If you take this and insert it up there as x1, this part here, and take this part, cx3 plus dx4, and insert it instead of x2 up here, and you just multiply things out, collect terms, you'll get to this. So basically what you have is that you consider the usual multiplication. You have x1 with x3, x1 with x4. That's the first terms down here. And you have the corresponding coefficients outside in front. Because constants just go outside the integral. So it's the usual definitions, but it's very nice to just find a place where you have this line written, because you will be needing it. Likewise, for the variance, you can do the same thing. We just discussed that for the univariate case here. I will do the multivariate in a moment, but remembering the square term. Now, in one of the exercises for today, you'll be asked to do the so-called second order moment representation. So that is not just the second order moment, which is the variance, but it's also the covariance if it's a multivariate system, and the mean value. So a moment representation up to a given order is describing all the moments up to that order. Usually we will restrict ourselves to second order because we are in a Gaussian world, so everything beyond that is zero. So we don't want to spend time on that. Now, when we then go for the multivariate case, well, the expectation of a vector, we'll treat that as the expectation of the individual elements. So each of these are integrals in theory. The variance, which we'll call the variance covariance matrix, which will be obvious for in a moment, is defined in the multivariate setting by x minus mu parentheses times x minus mu transpose. X minus mu is a vector, a column vector. You transpose it, you get a row vector, and you multiply it out, you get a matrix like this. So if you look at the individual elements, x1, x2, and so forth, in the first upper hand corner, you get the variance of x1. Then if you go down, you have the covariance between the second element of x with the first element, and so forth. So you have variances in the diagonal and covariances outside. That's also why we call it the variance covariance matrix. This is also, you can say, the definition for the standard normal, or the normal definition in the multivariate setting. If this is the identity matrix, all the different elements in the vector are independent, and they have the identical variance being equal to 1. So you have, in this case, n independent univariate normal distributions. That's the definition of a standard multivariate normal. It's kind of intuitive, right? But it also matches when we get to the detail. The definition of correlation, I assume you've seen this before, is the covariance divided by the square root of the variance of the two terms. Or sometimes written as sigma ij or sigma I multiplied by sigma j. You may also see that written as so sigma ij is an element up here. So that's a covariance element. You sometimes see sigma I here. You may also see, to make a variance, you square that. That's the usual way. But you may also see it sometimes written as sigma I. Using the covariance kind of notation there. That's a little bit of mind-boggling. When you have two indices here, it's actually a variance, don't need to square it. That's just one thing to mention. So when you just have a single index, you want to square it. The usual way of writing this is to, you can say here, to square each of these and take the square root. That's what you do. Take the square root of the product of the variances. Okay. So, correlation and independence, one step further. If x and y are independent stochastic variables, then the covariance between the two is equal to 0. And of course then also the correlation is equal to 0. However, you can construct cases where the covariance, as in this case, we have x and x squared. If you calculate the covariance of that by the calculation rule, you get x cubed, and the expectation of x cubed is equal to 0. So here we have something where the covariance is equal to 0, but the conditional expectation, they're not uncorrelated, since we have this structure. Of course they're not uncorrelated. If you know x, you also know x squared. I mean, it's quite obvious. But the covariance is 0. So independence implies no correlation and not the other way around. That's an important thing to just keep in mind. Often we will just assume that things worked out nice. Well, the reason is here we did a nonlinear transformation, and that is where things start to break down. We will tend to do linear things within this course. Of course, we will square terms at places, but we'll try to avoid this problem in general. So, when you have it for a multivariate setting here, the correlation matrix is basically just pulling all these correlation coefficients into a matrix. That's kind of obvious, that's how they're indexed. And we can also talk about the covariance between a p-dimensional x and a q-dimensional y. So they do not need to be the same dimension. That's also why you need to keep track of what to transpose and what not to transpose, to make sure that dimension matches. It's defined, the covariance in multivariate setting, in the usual way, x minus mu times mu minus nu transposed. So the last term is transposed because you have a column vector multiplied by a row vector. That gives you a matrix of appropriate dimension. Yeah, some calculation rules, but they are, you can say, just extensions of the univariate case, and the thing you have to keep track of is what to transpose. That's the main thing to keep track of. And of course, for the variance, it's the same thing. So you have the calculation rule that I mentioned before, that the variance of a constant times a stochastic variable is the constant pre-multiplied and post-multiplied transpose on that variable. I promised to give you some calculation rules for the conditional expectation. They are why over here. If you look at them, some of them are a little bit mind-boggling. At first, I will just try to say them in words now, but I know from my own learning of this that it's some things that you actually sometimes want to spend a little bit more time on. What is actually the meaning of that particular statement? The first one is easy. If x and y are independent, the conditional expectation, define that. Conditional expectation of y given that you know x is the expectation of y and then using the conditional density instead of just the density. And this is something that we will do repeatedly. Again, if x and y are independent, then by definition the conditional density is equal to the marginal density. And thus the expectation of y given x is the same as the expectation of y. Sometimes you think, why on earth do you want to do this? Well, sometimes it's difficult to calculate the expectation of y directly, but it might be easier to calculate the expectation of y, the conditional expectation of y given x. If you have a helper variable of some kind that is easy to handle the interior part here, then the interior part here becomes a function of x, and then you take the expectation with respect to x at the end. So you can use a helper, and the same thing, a similar thing applies if you multiply with some function of x and you still condition on x. Well, this is a constant then, because you condition on the value of the stochastic variable x. You don't know what it is, but relative to the expectation here, it's a constant. So you can take it outside the expectation. And this down here is basically the same as up here. You can do that again. Make the conditional expectation in here. Similar story. If it's easy to handle x, or the conditional value of expectation of y given x, this can help. This one is trivial. The expectation of a constant, that's a constant. No surprise. The conditional expectation of a function of x, given that you know x, is of course just the function of x. This is again still a stochastic variable, because I condition on a stochastic variable. And the conditional expectation of some of things given something, well, the expectation, as is the conditional expectation, is a linear operator. So we can split it in the same way as we did for the just expectation. Because basically the only difference is that instead of having the density of y in here, we have the conditional density of y given x. That's the main difference that is made. Yes?
In the fourth line, on the right-hand side, the outermost expectation, the right-hand side,
Yes?
is that necessary?
Yes. Because here I take the expectation of g of x and y. So this is not a stochastic variable. If I did not have the outer expectation here, then I would have the expectation of y given x multiplied by g of x. That would be a stochastic variable, but it depends on x. Does that make sense?
Yes.
But yeah, you have to keep track of where the expectations are. And there's a lot of parentheses here. I will get to that. But that's another nice page, at least until you get familiar with these calculation rules. It's a nice page. It's collected in the book on some page. These same equations. Conditional variance and covariance are, you can say, it's a trivial extension, you can say, because it's just doing the same thing as we did before, except on a condition on x. Everywhere there's an expectation, we just include condition on x, condition on x, condition on x. All the rest is the same, both for the variance and the covariance. You have to keep track of the covariance of y, z given x. Well, that's both y and z that are given x, conditional on x. So you have the one part related to y and the other part related to z, and then conditional on x at the very end. So this is something you can say you need to know the calculation rule. Often you will just handle the covariances as covariances. I'll give you an example in a moment. So, this is actually where I think also things are a little bit critical until you have done it a few times. You can separate the variance of something by using conditions. So you can take the variance of y and say, instead of calculating that directly, you can say what is the expectation of the conditional variance of y given x plus the variance of the expectation of y given x. Often referred to as the expectation of the variance plus the variance of the expectation, in brief. Why on earth do this? Well, it's the same story as here. Why on earth do stuff like this? Why do the expectation of a conditional expectation? Because it's sometimes easier if you can find a variable x, it's much easier to calculate what is the expectation of y given x. Well, that's a random variable that depends on x. Then it's just a variance of something that's related to x that you're calculating here. And here you have the variance of y given x. Well, that might also be easy to calculate. And you just take the expectation of that expression. And for the covariance, you can do the similar expression. It's the expectation of the covariance plus the covariance of the expectations. Those are some expressions. I mean, what helps you to learn this is to do that. It's one of those things that if you've done it a number of times, well, okay, now it's okay. The reason why it works is due to some, you could say, orthogonal ideas, but that's another thing. Linear projections, this is one of the places where there's a drawing in the book that is quite abstract. So I'll try to use some other words than what is in the book. So, if you have two random vectors, x and y, or y and x, you can collect them and treat them as a bivariate vector, and each of them may actually, I think it's everywhere written so that y and x may also be vectors. So what happens then? We have the mean structure and you have the variance covariance matrix. Notice the subscript up here. So sigma yy is the variance covariance matrix of y, sigma xx is the variance covariance matrix of x, and sigma xy is the covariance between x and y, and sigma yx is the covariance between y and x. What holds for those two matrices? Can you see that? Sorry? There is some symmetry here, but the symmetry goes for the entire matrix. It has to be symmetric. But that submatrix there, if the whole matrix here has to be symmetric, what happens? What has to hold for this matrix and that matrix there?
They'll be transposed.
Yes. So they are each other's transpose. So sigma xy is equal to the transpose of sigma yx. What just happened there? What is making that noise?
It's
cooling. No, it says it's powering on down here. Whatever. I had to turn it on to turn on the PC there. That's the only way I could do that. I'll turn off the sound in a moment. So that's the definition of the system. Then we'll define the linear projection as rho x. We'll define that as the rho x of y So we'll make the projection of y down to x. We'll find that as the mean value of y plus the covariance matrix between y and x times the inverse of the covariance matrix, or variance of x. I may sometimes say the covariance between x and x. This is the variance or variance covariance matrix of x. I will often just call it the variance as the multivariate generalization times x. Something wrong here. Where is the typo? I have to update the slide. I think something odd. X and Y. No, that's not better. The function x. Okay. For the given value of x. So this is the definition of the projection. You start somewhere and then you update it by making this projection. If you look at this, the form here is a linear projection. You can also have some constant terms, one that comes from here and one that comes from the new x there, and then you have a function of x as well. So it's on the form of a plus bx. If you look at the variance of this, well, if you look at the variance of what you have up there, you can see that you have the variance of y that comes sort of from this, and then you have this out here that gives you a covariance term. I won't go through that, but what I will go through is the covariance of y minus this projection onto x. How is the, you can say, what is the difference between the point where you project to and y and x where you make the projection to? So consider x to be a plane, and then you have y as being point out there, and then it's just a projection onto that plane. So if we want to do this, we have the definition up here. If we do go for the covariance of y minus rho x of y, comma x, well, let's first just write it all out. That means we just insert here the definition we have for up here, so it becomes the covariance of y minus what we define up here, mu y plus sigma yx, sigma x inverse x minus mu x, like this, comma x. Now we first have a look at this and say, are there anything that we can get rid of? We do have some constants. Mu y here, and we also have a mu x here with some terms. So the first thing is to say is the covariance of the non-constant terms. We have a y from there, this goes out, and then we have an x in here, so that becomes a, oops, that should be a minus, because there was plus up there and it's inside a parenthesis. So it's a minus sigma x y, sigma xx inverse on x, comma x, like that. Now, we have an operator here where underneath is an expectation, so we can take the individual terms by the equation that we showed a long time ago, the covariance of ax plus bz, comma something else. You just multiply out that product. So this here equals the covariance of y, comma x minus the constant coefficient out here, sigma xy, sigma x inverse, and then the covariance of x comma x now. Well, we have a different notation for this, being sigma y x, and when we look at this here, sigma xy, sigma xx. Does it transpose? Maybe that one. That should be a yx. Where did I make that typo? It says y up there, so, and therefore it should be yx, and there I swap the order, yx, 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 sigma xx inverse, and then the covariance of x with itself is sigma xx. And you can easily see that those two terms are cancelled out. So what we're left with down here is sigma yx minus sigma yx equal to 0, as we wanted it to be. So, similar to before, I will show you when these are not the case that we want, but we'll treat it generally as a nice thing. So what it does, the linear projection, is that it minimizes the variance among linear functions that are that gives projection errors that are uncorrelated with x. That's what we did down here. The projection error, as in y minus the projection, is uncorrelated with x, meaning it's orthogonal to the plane where we are projecting onto. If x and y are multivariate normal, this is the property of y condition on x. So that's the definition that we will use. The conditional value of y given x instead of this here. But I won't write expectation of y given x equal to here, because there are cases where it does not hold. Take the example from before where we had x squared. The expectation of x squared given x is of course x squared. But if I do the calculation for the linear projection, I get a 1. So they are not the same, always. The reason is x squared here is not multivariate normal. If you take a number that is normally distributed and square it, it's not normally distributed anymore. So when things are normally distributed, it does hold that the expectation of y given x is the same as the linear projection, otherwise not. So we will write this pretty much all the way through this course. And, well, most people do so. When things are normal, it works. And calculation rules are the same. So we'll go forward as that. but keep in mind that things should be normally distributed for that to hold. Now I will quickly run through an example touching upon many of these things. It's data from Jagtvej in Copenhagen. In this case, quite old data. I will show you some newer data later on. They made measurements of NO and NO2 combined to be NOx, which assume that everyone knows more about these days than a couple of years back when people did not talk about cars and things that are sort of fraught. In this particular setup, we assume that we have measurement every third hour. And we have the global mean value for the NO2 part to be 48 micrograms per cubic meter and NO to be 79 micrograms per cubic meter. And we will, just to tease a little bit, have x1 to be how does NO2 deviate from the mean value, and x2 to be how does NO deviate from the mean value. So that's the definition of the system. Well, why do I make this small transformation down there? Well, I transform the system to the stochastic variables x1 and x2 have mean 0. It makes a lot of calculations easier. That's the only purpose. And without loss of generality, I will do that many times throughout the course. You can just add the mean value later. So, through some investigation, they figured out that this model is adequately describing the system. So the state, get that by taking the previous state, multiply that by a constant matrix, and then there is some noise. And the noise is a multivariate Gaussian, zero mean, and this variance covariance matrix here. Or we can also write it on a matrix form, of course. So let's assume that 9 o'clock today we had the following measurements. And then what we want to do is to say, what happens at noon? What is our expectation for noon? We should forecast the concentration. How do we do that? Any ideas based on what we talked about today? There's another thing we need to do. We need to find the variance covariance of that forecast as well, because just the point value, as said as in introduction, does not provide any insight. It's just a value that we know we will never get. What we'll do is to make the best predictor, which is the conditional expectation. So we make the conditional expectation of x at time t plus 1, given the information that we have up to time t, which is summarized in these two variables. So the forecast is the conditional expectation of xt plus 1 given xt. We will plug in the process here. And now when we look at this, what is the expectation, or conditional expectation of phi xt plus epsilon t plus 1? Let's take them one term at a time before showing it up here. Well, phi is a constant. We move that outside. The expectation of xt given xt is just xt exactly. The expectation of epsilon t plus 1 given xt, 0 exactly. So the expectation of a future noise, assuming that things are independent, which is what we usually assume, is 0. That was quite easy because we know that. We just have to multiply that with a 2 by 2 matrix. Now for the variance, we need to look at this. What is the variance of the value minus the expected value? we can plug in again, plug in the expected value. This term here, the phi x term, cancel out with the other phi x term, and we're left with the variance of the epsilon t plus 1 condition on xt. Now, what we just assumed before, or was said, was that the variance, the future noise, does not depend on the state. So it's just the covariance matrix of the innovations or the system noise, as I will call it later. So that was quite easy. I will use R many times throughout this course. I will also do some things live. For now, it's just in a slide. You can also use MATLAB if that's your preferred language. There's a few things that where you almost have to go to R, but you can get by with MATLAB for most things. But I will use R throughout what I present. So these are just the calculations to get to these values. I have to define the variables. I have to make what is the t plus 1 prediction, the hat operator. I'll show that. I'll discuss that later, why I use the hat as an estimator. So this is the expectation of xt plus 1 given xt. And I'll use the hat instead of, let me just write it, that I will say that x hat t plus 1, that's my shorthand notation of the expectation of xt plus 1, well, given t, given xt. So I'll use that shorthand notation repeatedly. Well, that from the previous slide, it's just phi times xt, and then to get back to the domain where the measurements are, we need to add the mean value. So that is our prediction. Now, at noon, for some reason, only the NO2 concentration was measured. For some reason, NO failed. So, what do? We need to make an estimate of the NO. We made one just before, 96.6. Can we do better than that? Well, we just got a measurement of the NO2. So we got some information that we did not have when we made the previous prediction. So hopefully we will be able to do something better. Can you guess what is the appropriate thing to do? Are the NO and NO2 states dependent or independent? Are they dependent or independent?
They're at least correlated.
They're at least correlated, so they're not independent. So that means when you get information about one, you also get some information about the other. So we should be able to improve. So, we'll just write it up. The conditional expectation of x2, the missing observation, given the observation that we did get, and all the previous information that we had. Here is just writing it as an extra parenthesis in there and two conditions, but it's the same thing. Well, the conditional expectation. Let's try to do a linear projection approach to this. And this is where you probably want to go home and kind of look at every single step here, every term, and match that with the expression that we have down here. Because there's a lot of different conditions and things out there. And I'll try to walk you through it now, but I mean, it's a little bit dense. I'll give you that. But it's basically it's just doing what is down here, where everything is conditioned on xt as well. So what we have down here is the mean value of y, that is the expectation of x2, but it's conditioned on the previous observations as well. And then comes the covariance of y comma x, that's the covariance between x1 and x2 at t plus 1, given all the previous information. Then we have the inverse of the variance of x1 given xt at time t plus 1 given xt. And then we have x1 at time t plus 1 minus the expectation of x1 at time t plus 1 given xt, as we have done here. So far, so good. Now what happens from this here to the next is that we plug in values. The expectation of x2 at time t plus 1 given xt, that is the prediction that we had from before. Now I just take out the relevant elements of the matrix phi here. So it's the first row of phi multiplied on the x1 and x2 states from before. So that is the number that we predicted just before. And then comes the covariance between x1 and x2. We have that there. The variance of x1 we have there. And then comes inverse, the observed value of x1 at time t plus 1 minus the expectation of x1. Well, that's the second row we have down there. Right? So that's what we get. And the variance of this prediction error is defined as follows. It's the variance that was predicted. It's the variance of x2 at time t plus 1 given xt minus the covariance between the two predicted numbers in the prediction squared times the inverse of the variance of the prediction of x, also written as down here. If I insert numbers, I get a prediction to being 102.9, and the variance is only 0.95. If I scroll back a little bit, remembering the variance of being 0.95, the uncertainty in the system here is much greater than that. So we got a very large, in the prediction from before, the variance of the x2 state was 23. Now by observing the other observation, we could reduce the variance from 23 to 0.9. That's a rather large reduction. It comes from the fact that the correlation or covariance between the two states is quite high. It's almost equal to the variance here, right? Can anyone tell me what is the correlation between the two? We have all the information in that matrix there.
21 divided by the square root of 30 times 23.
Yes. What is that value? (21) divided by the square root of 30 times 23. It's beyond what I can do in a split second in my head. My guess would be 0.9, but that's a guess. I did not actually calculate it. Anyone? How long time does it take to
21 divided by the square root of
21 divided by the square root of the product of the variances? The square root of 30 times 23.
0.8.
And what is the next digit?
0.799.
Okay, 0.8. Fair enough. So quite high correlation. And that is the reason the covariance here, which is related to the correlation, is quite high. So you take the prediction variance, which was 23, and then you subtract this number here, whereas that is the covariance squared divided by the variance of x. So if the NO2 observation has very little uncertainty, then you make a large, and they are very much correlated, then you make a large reduction in the covariance here. That's the idea. And that also makes intuitive sense. If you have two things that have a high correlation or covariance, and what you observe has a not too big variance relative to the covariance, well, then you get a lot of information about the other states by just observing one of them. So, that's that story. This, and I'll try to do that at the end of every lecture, is just a slide containing what I think are the highlights, the essential things from today. I did include the calculation rules for covariances, also the variance separation theorem, and the linear projection as it is, and just saying what is the moment representation. And then from now till noon, I'll ask you to work on exercises 2.1, 2.2, and 2.3. And as said initially, for those of you who cannot find a seat in here, I have an extra room, but if we can all fit in here, we might as well just be all of us in here. Because at least, I don't know, how do you feel the air in here? For me, it's fine. So it's fine to be all of us in here. But we'll see how that goes and then take it from there. I should say one thing regarding... One more thing! I heard... I can easily speak up much louder than this. Exercises and all that is also in CampusNet in the calendar, where you also see what is the schedule for next week and so forth. So, yes, thank you for now.